Let's dive right into this explainer and investigate what is, honestly, a truly fascinating mystery. We're going to look at whether a 50-year-old vintage computer model accurately predicted the defining challenges of our current decade. We are looking at a story that bridges the dawn of early computing, the massive engine of global economics, and ultimately, our very survival as a species. It's a narrative that starts way back with those massive, room-sized mainframes crunching numbers on punch cards and leads right up to the modern climate and economic data that we see on the news every single day. Did a computer from the 1970s actually predict global collapse by 2030? Wow! That striking question is going to drive our entire journey today, as we unpack the hard data behind one of the most famous and fiercely debated scientific warnings in history. Back in the early 1970s, at the absolute dawn of the computing age, a group of really bold researchers asked a machine to map out the future of human civilization. And the answers it spat out were genuinely shocking. Now, for decades, critics just brushed those answers off, calling them overly pessimistic or fundamentally flawed. But today, with a half-century of hard, real-world data to look back on, we really have to ask, was that vintage computer actually right all along? Think about the whaling industry for just a second. A Japanese journalist once famously noted that you might think of the whaling industry as an organization interested in maintaining whales, but actually, it's better viewed as a huge quantity of capital attempting to earn the highest possible return. And that hits the nail on the head, right? Human systems often relentlessly pursue their own specific, mathematically driven goals, even if those goals lead straight to eventual depletion. A system designed to maximize profit is going to do exactly that, right up until the resource it relies on vanishes entirely. This massive disconnect between what we assume a system is doing and what it's actually programmed to do is absolutely crucial to everything we're going to cover today.
So, let's start with part 1, the 1972 warning.
This study was an absolute watershed moment in science. Based on the pioneering work of MIT researchers commissioned by a group called the Club of Rome, this project utilized a massive computer model named World 3. Now, we need to be clear, this wasn't some magical crystal ball. It was a rigorous calculator. The model meticulously tracked the complex, real-world interactions between global population, non-renewable resources, pollution, agricultural production, and industrial output to forecast our collective future. They basically wanted to answer one fundamental question: what happens if humanity simply keeps expanding our economy and our consumption on a planet that has strict, finite boundaries? Ultimately, the model spat out two dramatically different primary outcomes, posing a stark choice for humanity. If society just kept pushing for unchecked infinite growth, the computer showed we'd hit a scenario called overshoot and collapse. And yeah, that is exactly as bad as it sounds. We grow far beyond the Earth's carrying capacity, leading to a sharp, painful drop in living standards and population as resources simply dry up. Conversely, if humanity consciously shifted its priorities toward health, education, and extreme resource efficiency, we could achieve a stabilized world. Basically, we either crash into the wall or we gracefully hit the brakes.
Which brings us to part 2, understanding system dynamics.
To grasp how the computer actually got these answers, we really need to talk about J. Wright Forrester. The guy is a literal legend. He actually invented the magnetic core memory that made early random access computer memory possible. But later on, he turned his immense genius from electrical circuits to social systems. Forrester realized that our standard way of solving problems through political debate is fundamentally flawed. Because our minds constantly shift assumptions mid-debate, we rely on fuzzy, imprecise mental models. As Forrester rightly pointed out, human brains are frankly pretty terrible at calculating multiple interacting variables over long time delays. We desperately need rigorous mathematical modeling to truly grasp how complex global forces interact with each other.
The absolute central pillar of Forrester's work is the feedback loop,
A feedback loop happens when a change in something eventually circles back to cause a further change in that exact same thing. Take a second to really digest that, because getting a grip on this concept is totally non-negotiable if you want to understand why our world behaves the way it does. Our global environment isn't just a straight, predictable line. It's a massive, incredibly complex web of these feedback loops, constantly dictating our growth and eventually our decline.
Now, there are two main types of loops we need to look at, and understanding them helps us instantly see why technology isn't just a magical instant fix for everything. First, you have reinforcing loops, which cause runaway exponential growth. Think of a population multiplying endlessly. But then you have balancing loops. These actively seek a goal, just like a thermostat turning off the heat when a room gets warm. And here's the kicker. Balancing loops inherently involve delays. By the time a thermostat actually registers the heat, the radiator is already boiling hot, so the room overshoots its target temperature. Now apply that massive delay to the whole planet. When our global system finally realizes it needs to correct itself, say by drastically reducing pollution, it's often way too late. We overshoot the limit, the environment degrades, and the system collapses.
Okay, part 3. Checking the data today.
For decades, critics just casually brushed off this model as way too pessimistic. They confidently assumed that free markets and human innovation would just seamlessly fix any resource shortages without any dangerous delay. But recently, a sustainability researcher named Gaia Harrington stepped in as our modern, data-driven detective. She took those original 1970s mathematical scenarios and compared them against hard empirical data from academia, UN entities, and the World Bank all the way up to 2019. It's the ultimate reality check for our civilization. Has humanity done better over the last 50 years, or are we still stubbornly following that vintage computer's path toward collapse?
She meticulously mapped our current real-world data against 4 specific pathways to see which one our reality mirrors the closest. First, you have BAU, business as usual, which leads straight to resource depletion. Then there's BAU2. This scenario assumes we miraculously find double the resources, but that just means we keep growing until pollution and climate change cause a severe breakdown instead. Next is CT, the comprehensive technology scenario, where unprecedented innovation averts a total collapse, but the tech becomes so staggeringly expensive that health and agriculture decline anyway. And finally, SW, the stabilized world, where we actually change our values to avoid collapse entirely.
And the verdict? Well, it's incredibly sobering.
The data shows we are tracking closest with BAU2 and CT. This means our growth is highly likely to stall out within the next 2 decades, driven either by the massive financial cost of trying to innovate our way out of trouble, or an overwhelming pollution and climate crisis. And perhaps the most critical takeaway here, that ideal stabilized world scenario, the one where we consciously choose to limit our footprint for the greater good, is the path we are following the absolute least. We are actively having limits imposed upon us by physics and biology rather than maturely choosing them ourselves. All right, let's look at part 4, the giant leap forward. Now, while the window for a naturally stabilized world is closing fast, a 2022 initiative called Earth for All proves a deliberate trajectory change is still mathematically possible. Using an upgraded computer simulation based on the original World 3, researchers discovered something highly surprising. Human population is actually expected to peak in the mid-21st century and then naturally decline. So the real mathematical driver pushing us past our planetary boundaries isn't the total number of people on Earth, it's actually the immense material consumption of the wealthiest 10%. By identifying this, the math shows us that shifting our societal priorities away from pure material consumption can actively alter the trajectory of our future.
To actually achieve sustainable prosperity on a finite planet, the Earth for All model requires 5 extraordinary policy turnarounds to be implemented simultaneously. It's not enough to just slap some solar panels on roofs and switch to electric cars. We have to systemically eliminate poverty, vastly reduce extreme inequality, and globally empower women, which, by the way, directly impacts demographics, education, and workforce stability. We also must completely overhaul how we grow food and distribute global wealth. The computer model definitively shows that if you pull all 5 of these massive levers at the exact same time, the math actually works out in our favor.
So, humanity is really facing an ultimate mathematical choice right now. If we stick to our current sluggish policies, what the model calls the too little, too late track, it forecasts severe social breakdown, rising inequality, and immense social tension as resources become painfully strained. But if we can orchestrate rapid global cooperation to enact those 5 turnarounds simultaneously, we initiate the giant leap scenario. In this model, global temperatures stabilize, extreme poverty ends, and human well-being actually rises across the board, all while sharply reducing our material footprint. It transforms those scary statistical warnings into an actual, actionable roadmap for survival.
What you should really take away from all this is that those computer models from the 1970s, they weren't just some crazy doomsday prophecies. They were incredibly accurate, rigorous maps of system dynamics. They showed us decades ago that endless physical growth on a finite planet is literally mathematically impossible. We are now rapidly running out of the ability to cope through delays and technological bandages. Thank you for joining me for this explainer today. I want to leave you to ponder one final thought as we watch the real-time data unfold over this absolutely critical next decade. Will we change our priorities in time to make the giant leap? It's not too late to rewrite the code of our future, but the clock is certainly ticking.